Okay, so indeed, I'm going to talk today about naked singularities for the Einstein vacuum equations. I'm going to start the talk just by reviewing a concept that, of course, everyone in the audience or most people in the audience will be familiar with, but just I'd like to go through it quickly, just as an opportunity maybe to make some sort of philosophical points and fix some notation. Okay, so the weak cosmic censorship conjecture. So this, so what is the weak cosmic censorship conjecture? It's a conjecture which underlies basically, entirely how we think about, say, classical relativity in 3+1 dimensions. And formally, it states the following thing. If our initial data for solving the Einstein vacuum equations are complete, regular, and asymptotically flat, then, okay, of course, we know that singularities can emerge, like in various famous examples, but generically, at least, they're supposed to always be stuck inside of a black hole. And so if we don't want to deal with them, we sort of don't have to deal with them. Okay, so a few quick remarks about this. So I think sort of an interesting point to make is that, as far as I understand, at the time of the original formulation of this, really the only evidence for this is that, all known explicit examples satisfy the conjecture, and then kind of, it would be really nice if it was true. And somehow it's only really because of some work, which I'll quickly sort of review later, some work by Christodoulou for a model system, the spherically symmetric scalar field system, that it was even understood, in principle, in that simpler setting, sort of what a heuristic mechanism by which, a reason that this might even be true. And furthermore, it was only because of that work that we sort of, now, when you hear this conjecture, people will just say generically, but it's really only because of this work that we even know that it's reasonable to that you should put in the word generically. Okay, then a final point is there are these words that have appeared in the statement: regular and singularities. These are, I've stated them in this vague way, but of course, it's tremendously important to make precise what you mean by these, and depending on how you decide to formalize the notions, it certainly, in principle, can change the validity of the statement. So this is perhaps more familiar, and we've seen references to this already in previous talks, and I think according to the schedule, we'll hear more about this later, that sort of, for example, in strong cosmic censorship, this is exactly what you mean by regular plays a very important role. So it's somehow you can make the analogous, it's kind of an analogous situation here. Okay, and so that being said, maybe let me take the opportunity to have a brief sort of philosophical digression about what should I mean by regular initial data and what should singularity mean. I don't want to get too derailed, but sort of since I've opened the Pandora's box by discussing this, let me just say a few things. So first of all, of course, the easiest thing is to say that we have regular initial data if our initial data is smooth, and then you're singular if you're not smooth. And in many contexts in physics and mathematics, that's a perfectly acceptable framework, but I would claim in reality it's a bit naive from various perspectives. And what I'll say though, we do have, it's not that being said, it's not that you can work, of course, with in any random functional framework we want. There are some necessary conditions. I'll just list just a few just to orient ourselves. So maybe fundamental one is that whatever space we're working in, we want to claim that we've discovered a solution which corresponds to singularity formation. We want there to be some kind of well-posed Cauchy problem in that space. Right? That's pretty fundamental. But just to emphasize that that's not per se the only thing that you want. There's some phenomenology that we sort of know and love and sort of better be true. And if you can't understand it in your framework, it's probably a bad framework. So just as a quick example, if it's impossible to understand stability of Minkowski space in the framework you're studying, it's probably not a good framework. Okay, but that's sort of, let's leave that for now. Okay, so now the next thing I want to do is just, again, so we're all on the same page, even though I assume that people are familiar with the concept, let me say more precisely what I mean by a naked singularity. Okay, so again, and I'm going to work in this case, it will be convenient and it's not such a big deal to work with a characteristic initial data. So data posed on say on an outgoing light cone instead of space-like data. But that's not nothing that I'm saying in the talk that is that really such a fundamental constraint. Okay, but in this context, so again, we have some asymptotically flat cone with regular initial data with all the caveats that I said. So you come up with some framework of regular. And then we have a singular point in our spacetime. Again, whatever you decide singular means, which we assume that you've justified in some way, then the singularity is naked. Why is it naked? If as you go out on this asymptotically flat cone, farther and farther out to the where it becomes sort of as it converges to a Minkowski cone, and you sort of send in going null geodesics, sort of suitably normalized, they always hit the future light cone of the singularity, say, in a fixed finite time. So in that sense, no matter how far you go out, I mean, this is the formal sense in which how to say that there's no black hole which closes it. So no matter what, you sort of have to stop the space-time in finite time, and you need to understand anything global about the solution, you need to figure out what's up with the singularity. You absolutely cannot ignore it. This is sort of the bad situation. Okay, so hopefully that's clear. All right, so having done that, now I want to quickly go back to this. I referenced this work of Christodoulou, which is really the source of all the main intuition that we have, at least sort of heuristic mechanisms by which cosmic censorship might be true, and the need for this generically, the statement of genericity. Okay, and so what was this? So like I said, he studied the problem of weak cosmic censorship in this model situation, this spherically symmetric Einstein scalar field system. Okay, we all know that's a sort of classic toy problem to address various questions. That's a lot simpler than the Einstein vacuum equations, but nevertheless, in practice, yields lots of important intuition. And the main results were the following. So first of all, there do exist naked singularities for the system. Again, was not something that was clear beforehand. However, generically, they do not occur. So again, we still get sort of weak cosmic censorship. Okay. All right, and I'll say more about his solutions later, but I also just want to, I think to give a talk with the title that I have, it would be strange if I didn't at least just mention, of course, there's also this enormous world, a very important world, heuristic, numerical literature on naked singularities associated to what's known as critical phenomena, starting with the famous work of Shlapentokh. Those naked singularities turn out are not the ones that are going to be so relevant for my talk. So I'm not going to really discuss them. But anyway, I just wanted to mention them because that's an enormously important world. Okay. Anyway, so Christodoulou had this result, but somehow, all right. So that was done in the 90s, but until sort of recently, there wasn't really progress on sort of doing some kind of analogous construction for the vacuum equations. So why? Well, there are various reasons. So first of all, you can look if you really just focus on explicitly what Christodoulou did, it was important. So first of all, it's already imposed spherical symmetry that cuts down the degrees of freedom in the system quite severely. Then he imposed a certain kind of twisted self-similarity to the solution. I'll say something more about that before. And now sort of things really collapse when you do all of that. And the entire system becomes a two-dimensional autonomous system for which you can analyze the phase plane, et cetera, et cetera. It's still not an easy problem to understand, but it's sort of this kind of reduction was crucial to how to Christodoulou's analysis. So for the Einstein vacuum equations, there's no such, you can't carry out, there's no way to have such a sort of dramatic reduction that's compatible with sort of asymptotic flatness. So you need sort of a different approach. Okay, and given that, the sort of, if you try to understand it sort of dynamically in some sense, cook up some initial data to see a singularity emerge or whatever, you sort of have kind of what's somehow the kind of familiar difficulty. That is it's a low regularity problem. There's a singularity. You also expect that somehow so therefore some things will be large. But on the other hand, there's an aspect of the problem which is sort of a global existence problem, or maybe more precisely semi-global existence problem that you have to construct. You have to show that a black hole doesn't emerge. I have to show that picture I drew of a naked singularity occurs. So there's somehow I need to control there's a certain global thing I need to do, but on the other hand, things are large, it's a singular. And so there's this tension between these two gives it kind of the math, its characteristic flavor. Okay. So nevertheless, despite these, we sort of have naked singularities for the Einstein vacuum equations, which moreover, as I'll make the claim, there exist solutions which you can really think are in many ways qualitatively analogous to Christodoulou solutions. All right, so that's what I want to talk about. And so in the rest of the talk, so they're going to be sort of two parts to the rest. I first, because of this claim that I made that these naked singularities in vacuum are really qualitatively analogous to Christodoulou solutions, I want to take just some time to explore his solutions in a little more detail, and then I'll sort of present Igor and I's naked singularities, and sort of I will, and it'll be kind of presented as like a search for, if you were going about trying to find the analogs of Christodoulou, how would you sort of stumble upon this? I think that's a good way to try to understand it. Okay, so maybe that's a good time to pause. Any questions so far? No? Okay, so Christodoulou solutions. Okay, so first of all, he studied the spherically symmetric Einstein scalar field system. So what is this? You can think that it's described by a triple. So originally we have, of course, a 3+1 dimensional spacetime. We have spherical symmetry, so we quotient out by that. So we have a 1+1 dimensional spacetime. We have a metric h on there. We have the area radius function, which at any point tells you the area of the sphere it lies on. And then we have our scalar field. Okay. There are two sort of very natural central symmetries in this problem. Well, somehow the first is the most natural and most central, which is the basic rescaling symmetry. So this is for any positive real number, I can rescale my unknowns in this fashion. It's the rescaling that we all know and love. That's familiar in many problems. Okay, that's the first important symmetry. Then there's the other symmetry, which is kind of, in many cases is a trivial one and is not that interesting, but it turns out to be very important here, which is the fact that since we're studying massless scalar field, solution of the wave equation, I can add a constant to my scalar field and that doesn't change anything. All right, so usually that's not that interesting. Okay, and then this leads to sort of this definition of K self-similarity, which plays an important role. Okay, so which is what? So we say we're K self-similar if you can have a one parameter family of diffeomorphisms, i.e. coordinate changes, so that if you want, when you zoom in, you do a coordinate change and sort of look in at your space-time, you end up seeing all right, so the naive thing, the naive notion of sort of self-similar would be you zoom in and you see a rescaled copy of your space-time. But what we allow, this K self-similarity, is that we allow it to couple a bit to this translational symmetry, so that, okay, we zoom in, then we see something rescaled, but the scalar field might have been shifted by some constant depending on the rescaling, and the coupling between them is determined by this parameter K. We call it K self-similar. All right, we put the log. The log is just to make the two group actions compatible, right? Okay, so then in sort of following Christodoulou's terminology, if the simple case where K is 0, or the simpler case where K is 0, we'll call those scale invariant. All right, so this is a natural kind of general notion of self-similarity to impose when studying the scalar field system in spherical symmetry. Okay, so that's great. So it turns out that, again, we're already spherically symmetric. So when you impose scale invariance, it's really a lot of, there's quite a bit of symmetry you put on the system, and you end up, you can actually just write down the solutions explicitly. So I've drawn the picture here of what you see, sort of the small data solutions. Okay, so and it's kind of an amusing picture. So what happens is you have the origin. You have sort of there's the scale there. That's where your dilation symmetry is centered. The white dot right here. And what happens is, to the pass of this point, you have to be flat. There's nothing going on. And then when you cross the pass light cone of this point, the derivative of the scale, if you want to get something non-trivial, you have to allow for the derivative of the scalar field to jump. Okay, and then you get then there's something non-trivial in this region. And then what's amusing is that sort of there's a bounce, and then to the future of this point, it's again completely flat. Okay, so the derivative jumps. So of course these are not smooth solutions, but again, like I said, we're adults. We're not scared of things that are not smooth. And if you sort of look at these for a little bit, you realize there's nothing pathological about these. These are perfectly nice solutions, and they correspond to spherical impulsive waves. And there's no there's not, again, suitably interpreted. There's no sense in which these are relevant for the study of naked singularities. So that's sort of a kind of a dead end if that was the goal. Though they're interesting for other reasons, which one of which I'll say right now, which is Christodoulou also, he was interested in well-posedness in sort of spaces of low regularity, and he was able to establish such a statement for the class of so-called solutions of bounded variation. Now, I'm not going to, for sake of time, I'm not going to say too much about that, but I'll say one way that I like to think of what this means is that so if you have a smooth space-time and you zoom in on a point, eventually you're going to see a flat space, right? If you do the rescaling. So the bounded variation solutions, they're not smooth. So when you rescale, say at the axis of symmetry, you don't necessarily see a Minkowski space in the limit, but what you see is one of these scale invariant ones, which I sort of asserted to you were not that bad. So somehow this is the idea that they're singular, but they're sort of modeled on their singularities are these nice kind of singularities. Okay, so we have some well-posedness in this setting. Okay. All right, so now what happens? So now let's turn on K. Let's go to the more complicated kind of self-similarity. And basically here, you can't write down this. It's no longer possible to sort of write down a clean analytic expression of the solution, but sort of Christodoulou did, sort of all the work and was able to find that, again, for certain values of K, and in fact, I'm writing here just less than 1, but actually, if you look at it has sharp thresholds for all these things. But what's relevant for us is just that if K is pretty small, then there's a solution with this Penrose diagram, which is familiar from what I drew near the beginning of the talk. It has the Penrose diagram, which looks like a naked singularity. Again, if I justify that the data is regular and say what I mean by the singularity, so he's able to find things that have sort of the right Penrose diagram. And why? Okay, and why could we, why is the regularity and singularity justified to call it a naked singularity? Well, for the following reasons. So it turns out that the regularity, the scalar field, again, it's not smooth, but it's C1 alpha, which turns out to be sort of better than what's required to be bounded variation. Remember, we have a good theory, well-posedness theory with it for solutions of bounded variation. So these are better than that. What about the singularity? So what sense is it a singularity? Well, it's impossible to extend to the singular point and remain a solution of bounded variation. And there are different ways that you can see that. I'll mention some just because just later, if there's time, and I wanted to draw some analogy. So some ways that you can see that for solutions that are important are there's Hawking mass concentration. So if you want, this is scale invariant energy concentration. You look at the Hawking mass divided by the area radius. That's a scale invariant quantity, measuring the sort of the energy in the sphere. This, if you're a regular solution, this should go to 0 when you go to the axis, but for these, it sort of concentrates. There's a positive contribution even when you go all the way to the axis. Maybe a more straightforward way that things are singular is that, well, the scalar field blows up logarithmically. In particular, the derivative of the scalar field when you integrate on v equals 0, the u derivative du, this is infinite. And I write that also to denote that that integral is, of course, reparameterization invariant. So there really is a geometric statement that blows up. Okay, a few sort of remarks. The first one is not so serious, but just just for scaling considerations, strictly speaking, any self-similar solution is not going to be asymptotically flat, which is what we want for a naked singularity. Just because of, for example, how the Hawking mass scales. But it turns out to be, it's very easy in the setting to once you have a solution which it essentially looks like what you want, it's quite easy to truncate it and make it asymptotically flat. So that's not a big deal. Then the last thing I want to say, this is again something which we'll sort of come back to later. What's interesting, it's very natural given what I've said is, okay, you say, so when K equals 0, we had some solutions, they were supposedly nice, non-pathological solution. Now you claim that when you turn on K a little bit, all of a sudden I get bad ones. So what's up as K goes to 0, right? Natural question. So it turns out, well, as you would expect, that's a singular limit. And in fact, even though in some sense you think of k as a small parameter, because k is small, it's a small parameter, it's your twisted self-similarity is not too twisted, but 1 over k then shows up, and that, for example, this thing is blocked, but d by dv of the scalar field, there'll be some points in the spacetime where this is proportional to 1 over the square root of k. So as k is going to 0, there are points where this is really, really enormous. Okay, so that's the deal with that. The questions? No? Okay. So that's Christodoulou, and now sort of for the rest of the talk, like I said, I want to so that's with that background, I want to present it in a somewhat revisionist fashion as sort of the search for analogs of Christodoulou and how you would sort of stumble upon the construction that we ended up using. Okay, so the first question you ask yourself is, okay, I want to find so I had this this definition in spherical symmetry, self-similar. So I want to do something similar in vacuum. All right. You know, in general, it's clear that self-similar means that you should have a conformal killing field, right? And that's not so mysterious. So some vector field k, so that Lie k of g is 2g. Okay, but you know, unfortunately, to study any problem in a serious way, you need to introduce some type of gauge, which you know might involve, and it's not clear how to work something that as general as possible. So just to get started, we try to work. We say let's work with a double null gauge. All right, so that's coordinate system like this. That's okay. Any solution can locally be put in such a gauge. So maybe it's a reasonable place to look. But what's certainly unclear is, all right, but in this gauge, if I have say conformal killing field, what does that field have to look like? There's not clear a priori, natural. So we do sort of on the basis of Minkowski space. Let's assume k is u du plus v dv, because that's what it is on Minkowski space. All right, so let's assume that generates a scaling symmetry. Okay. Okay, and again, so more sort of concretely, what does this conformal killing property imply? It just means that, all right, so there are these sort of 3 unknowns that build up our metric. We have the lapse function, omega. We have this g slash, which is this induced metric on the spheres and our double null foliation. We have the shift vector. All right, so being self-similar just means that these things they could be functions of uv and theta. So now basically, they're functions of v over u and theta, and then there's some power of u outside determined by scaling. That's sort of the most concretely what this means. Okay, and then so having decided to study such a thing, there's a very natural first sort of place to look to get something interesting, which is to look along v equals 0. This is the pass of the dilation symmetry. Because sorry, let me go back actually. So if you look at this vector field k. So of course, at v equals 0, it's just equal to u du, which points along v equals 0, right? So the point is, so if in particular, if you have an equation along the cone, because of the dilation invariance, it will become an equation just on a single sphere. So it's natural that we should do that. Let's take sort of everyone's favorite component of the Einstein equations, the Ricciardouri equation. It's like the ingoing Ricciardouri equation along the cone. That becomes an equation on the sphere. And that equation is this one that I wrote down. Okay, which doesn't, all right, so it doesn't maybe look so interesting at first. Seems like, fine, it's one equation. So this, and it appears to be quite underdetermined. So, okay, so you might think, okay, maybe this is effectively determining divergence to B. However, it's not obvious, but with some work, you can show that actually there's a lot of rigidity in this equation. Again, the short version of it is you can imagine that the left-hand side, there are divergences. They want to integrate to 0. But on the right-hand side, there's this, well, Ricciardouri is our favorite equation, right? Because it has the monotonicity that we all know and love. And this monotonicity is reflected, that's the square term in the self-similar reduction. That's what that is. And that doesn't want to integrate to 0. And somehow this tension ends up implying a lot of rigidity. And you get that, in fact, sort of basically B has to be sort of a killing field, annihilate everything. So that's already pretty rigid. And then this is also not, certainly not clear at first, but by invoking whatever, you do sort of a lot of work, and you can understand that, in fact, given this, after a further scale invariant coordinate change, which will keep you in a double null foliation and keep you self-similar, you can, without loss of generality, actually take the shift to be 0 along this, along v equals 0, the lapse to be 1, and this induced metric to actually just be the round metric. All right, so somehow it turns out to be absolutely no flexibility along v equals 0. You just have to be trivial. And this is really a special rigidity associated with 3+1. So again, so I'll just say, so for example, when you show this statement, it's very important, of course, you use that, for example, on that every metric on S2 is conformal to the round metric. So the analog of the statement in higher dimensions is completely false. There's a lot of flexibility. So a special thing in 3+1, excuse me, there's this rigidity associated with this. Okay, but that's fine. That's just a rigidity, say along v equals 0. That doesn't say that the whole solution has to be trivial. So okay, so we can still try to study these. But it turns out we don't have to start from scratch. So this is sort of interesting. So, and again, this is a very intriguing story, which I don't have time to go into completely, but I'll just say Pfefferman and Graham were interested in studying problems in conformal geometry. And along the way, they ended up classifying sort of formal power series solutions to exactly this sort of, well, it's in sort of a different gauge and sort of a different language a bit, but basically classifying these types of self-similar solutions. Of course, in reality, they were interested in higher dimensions, but sort of, along the way, for completeness, they also did the case of 3+1 dimensions, and so we have the result. So so we have some class of these formal solutions. So I've sort of drawn kind of a picture, kind of formally, where their expansions correspond to. Right. So we have the origin symmetry. We have this past light cone, and they're expansions in V over U. So sort of imagine this, expansions in this angle of this triangle. Okay, so so the first place where Igor and I got interested in it was to ask whether, for example, we can. So these are formal expansions, which in the analytic category they converge. We were interested, for example, in the smooth category. Could you show that they always correspond to actual solutions in a suitable region? And okay, and that was something that we were able to understand. And again, more and even more than just that, actual solutions exist sort of underlying this as some kind of quantitative way to control these from their initial data. Okay, details of that aren't too important, but just to say that, okay, so we have some notion, it's true that we have some rigidity along v equals 0, but still we're still able to build some class of kind of the self-similar solutions, at least locally. All right, this is of course still very, very far from any naked singularity, because that is a global notion, right? But okay, fine. So we have this. All right. Okay, so then the first thing, if we wanted to try to make a naked singularity, maybe the first thing you might ask is, what about extension to the past? Because remember, we want to get a complete cone. We want to have a nice initial cone with nice asymptotically flat data. All right, so here now the rigidity sort of comes back and again causes problems if your goal is to make a naked singularity. So basically, there's rigidity, and again, it's not clear what the most general statement is, but under all sorts of natural hypotheses about how you would, again, fill in the interior of this cone, sort of anything natural that you do, that at least I can think of, you can prove actually has to be flat. So, and again, this should remind us again of the situation with Christodoulou and the scale invariant solutions, which also had this, they had to be flat to the pass of the plane. And again, it turns out, and just like in that case, you can interpret this. So again, they're not smooth. You can interpret it as corresponding to, well, a self-similar spherical impulsive wave, which is being sent in and is collapsing at the origin. And there's no sense in which this is pathological or corresponds to sort of a naked singularity or anything like that. It is interesting in its own right, and actually, it's an interesting problem to try to understand the global structure of these. In other words, what happens after it bounces. But anyway, it seems not relevant for naked singularities. Okay. Okay, so given that problem, given that I pushed that analogy with the scale invariant, there's sort of a natural immediate question to ask, which is, well, okay, so it seems that somehow we stumbled into only studying the scale invariant solution. Is there some way to get to the analog of these twisted ones, the self-similar ones? All right, so let's think about that. So what would that mean in this context? Well, one way to think about it is the following. So because of this rigidity along v equals 0 that I discussed, all these sort of solutions based off Pfefferman and Graham have the following sort of geometric properties. So if you look at the past cone of the singular point, the vector field, which generates the scaling symmetry, is also the null generator of the cone, right? And when you think about that a bit, it's then very natural to say, okay, so then maybe a twisted self-similarity would be when it sort of turns a bit. That is to say, so in the top cone, you just sort of slide up the cone, and the geometry of your sections is rescaled. While on this bottom cone, you can say, okay, maybe it's not that I slide up and I rescale, but I slide up and I have to apply diffeomorphism and I rescale. So again, geometrically, it's a very natural notion to consider. And would seem to be analogous to kind of the twisting, before in the scalar field system, you zoom in and then shifting the scalar field. I mean, that corresponds to sort of doing a diffeomorphism on a section of the cone. That's a nice analogy. Okay. Okay, well, it's nice to sort of posit that, but supposedly there was this rigidity. So what's up with that? All right, so how are we going to break this rigidity? Well, and the key is to remember that, of course, at the very beginning, we made some choices. We didn't need to make all those choices. So let's revisit that. So, okay, so we were working in this double null coordinate system, and we had this k equals u du v dv was the generator of the scaling symmetry. All right, so now what I'm going to do something which looks a little weird at first. And I'm going to say, okay, now I'm going to allow actually for a singular lapse. So I'm not going to insist that the lapse extends to v equals 0. Of course, this looks very strange because I was concerned that I want something which is, I don't want to have something which is super irregular. All right, so that maybe looks a little weird, but what's the sort of saving, what saves us is, of course, that, all right, so it's fine. So this just means that in that the UV coordinates, my lapse won't extend, but there's be another coordinate system where I will extend to v equals 0. Right, and but in this new coordinate system, somehow things look a little more ugly. I shouldn't have moved my mouse. In that if you can rescale v, and you'll now extend, but now the self-similar field will change. So now the formulas aren't nice. So it's nice to keep both coordinates. So there's this original coordinate system where the formulas are the sort of standard self-similar formulas, but it's not regular to v equals 0. And then I have this other one where I'm regular to v equals 0, but the formulas are not as nice. So this is sort of the key idea. And why? What's the point of this? The point, it's not too hard to explain, actually. So the point is just going back to this this constraint equation. This was the Ricciarduri equation. If you consider this notion with this this kappa, you allow this lapse to be singular in those UV coordinates. Then when you work out what Ricciarduri becomes in the regular coordinate system on v hat equals 0, an extra 4 kappa pops out here. And what you see is, again, if you remember that I had made this claim that where the rigidity was coming from is that the left-hand side, this divergence of v wants to integrate to 0, but the right-hand side has this positive term. This kappa here allows you to sort of impose sort of orthogonality condition. You can make that integrate to 0, and it completely kills that problem. And so now you're able to get, now it sort of is what you would think that, you can basically put any g slash you want, any lapse, curl of b, and then this really becomes an equation for divergence of b, and sort of everything is fine. Okay, so that's great. But yeah, so that's great. But now you still want to say, okay, that's just about the constraint equations. But I still want to know, can I actually build a space-time even locally based on this? All right. Okay, and so this is sort of the next result. So we're able to, again, sort of in the spirit of the result that we had for the Pfefferman Graham spacetimes, we're able to sort of, again, embed this more complicated self-similarity into some kind of, again, locally in some region. All right. So, okay, so it's consistent. We can build spacetimes with the symmetry, at least little pieces of them. All right, but now we're kind of at a very sort of, it's kind of a fundamental point. We still haven't addressed somehow what's potentially the scariest aspect of this, which is, okay, so you would think, again, you have something singular, presumably your solution has largeness in it. And indeed it's true, though I haven't sort of given you technical details. It's true that there are some components. So if there's an epsilon, which governs the degree of your twisting, there's some components of the metric which have size 1 over epsilon. So there's some largeness in the solution. So why should you be able to, for example, construct an exterior region where there's no, how are you going to show that something bad doesn't happen? Because, the only, in practice, I'm studying Einstein vacuum equations because of their supercritical nature with respect to any available conserved quantities. We need some kind of smallness. There has to be some smallness in order to control it. All right, but the sort of the miracle is that we are, despite this difficulty, we are able to extend this data to some asymptotically flat data and construct an exterior region where nothing bad happens. And the key point is even though there is some largeness, we identify sort of some leading order kind of self-similar dynamics of this largeness. And again, if you fine tune exactly how you set up your data, you can set things up so that this naturally it ends up damping out. So, and then you can sort of in a self-similar way, and you can kind of subtract it off and then find some smallness in your system, which allows you to close. Okay, that's sort of the numerical, which allows this to work. Right, and then again, you have the various in this sort of to this future, you have the properties that I said you need to have in order to be a naked singularity, and that if you send out you go out in this asymptotically flat cone, you send in these ingoing null geodesics, they will all hit the light cone in sort of in time one. Okay, and then so I guess I'm running out of time, but then of course it's also we also want to extend to the past, and this we're in the progress in the process of doing, but it's also possible to show that you can extend your solution to the past, right? And again, this rigidity has been broken, so this won't be a flat extension, right? And so again, modulo me pitching that the regularity of these is suitable and the singularity is suitable. This then is the we have the general structure of the naked singularity that we wanted. Okay, in the last few minutes, let me say something about this. So, like I said, the kind of the 2-second version of these 2 slides, which I might not have time to go through all the way. The 2-second version is that at the end of the day, there is a strong qualitative agreement with Christodoulou's naked singularities. Right. So, what's the various ways that manifests itself? So first of all, regularity. So so Christodoulou solutions were Holder continuous. The scalar field is Holder continuous, right? And then they're spherically symmetric. So there's only, there's only the v direction. There's no, as far as this initial data on this null hypersurface goes. So for us, again, in this outgoing direction, there's again exactly a whole. We have this C1 gamma behavior of the metric. But of course, now they're also spherical directions. But the spherical directions are basically as regular as you want. So again, that's sort of you're sort of qualitatively you're takes many angular derivatives you want, and then the lack of regularity is really the same. The largeness of the initial data behavior is also very similar. So Christodoulou's, again, near this v equals 0, his scalar field have this 1 over k to the 1/2 behavior. Again, we have this very similar. Again, certain trace-free part of the outgoing derivative of g slash, i.e. chi hat, for those who know that terminology, is like 1 over epsilon. So and it's very, and the behavior of them is really analogous. Okay, there's sort of a quick one thing is that, of course, in Christodoulou's setting, I invoked he had this bounded variation, well posedness. There's not a strict analog of that which is available in the vacuum. However, in various situations, it has been understood that you can establish well posedness results for the Einstein vacuum equations, where you allow something can be say pretty irregular. A v derivative can be pretty irregular, say only be an L2, as long as if it's balanced by sort of sufficient angular regularity. And in fact, in the setting, we even have sort of extra Holder continuity over these other other situations which have been covered. And so it's natural sort of on the basis of what's been understood in other situations, in particular this work of Luke and Rodnianski with impulsive waves. It's natural to conjecture that there should be a well posedness statement which encompasses the kind of data that we study. And if it's all right, if I'll just take just a few more minutes. All right, so let me say something about the nature of the singularity. So okay, again, there's kind of standard ways that we when we draw these analogies. So certain derivatives of the scalar field correspond to certain components of the metric. We usually identify the dv derivative of the scalar field with the trace-free shear of the outgoing null hypersurfaces, and then d by du with the ingoing shear. And again, so that's just a sort of general thing, which is usually a good idea. And again, if you do that here, it turns out to really serve you well. So again, we have the analog of the scalar field not being the derivative not being integral. Again, it turns out a shear is also not along suitable null geodesics approaching the singularity is also not integrable, and that's also reparameterization invariant. So you have that analogy. You can also find Jacobi fields which blow up along suitable null geodesics. There's also, again, you can do a similar Hawking mass calculation, even though in outside of spherical symmetry, the Hawking is of course foliation dependent. But anyway, but you can still do it. You can still sort of capture in the natural foliation picked out by the self-similarity, the same Hawking mass calculation works. Okay, so all right, so and what you can say, I mean, it's a bit, it's hard to, I don't have something terribly precise, but these various statements are all formally consistent with it being a C0 singularity, the metric, even though we don't have sort of a formal statement to that in that direction. All right, and then maybe I'll just close with by preempting some of the natural questions that I'm usually always asked. So first of all, are these naked singularities unstable to trap surface formation? Yes, we believe so, and it's sort of clear from the fine tuning that has to go in the construction. You sort of see how and why they're unstable, and in many ways, it's analogous actually to the instability mechanism from Christodoulou's work on naked singularities. Okay, and so this is something we plan to study in the future. Are all naked singularities unstable? This remains sort of wide open. I don't think this construction per se doesn't really yield insight on that problem. You know, in the sense that you might expect that any given naked singularity you construct is maybe easy to show it's unstable, but but that sort of doesn't really get you closer to the general statement. And then finally, is it possible to construct naked singularities with smooth initial data for all sorts of reasons? One expects so, but that remains an open problem. All right, so I'll end there.